and it's going to be on novel approaches on robotic actuators and sensors. So I have to say that Concha is from my same institution, but although we knew each other somehow, this is the first time we met. Thanks, Monodon, for this opportunity. So Concha is director of the Center for Aeronautical Training and Services of the Universidad Carlos III de Madrid. For more than 20 years, he has been working on different research projects on robotics and robot control, especially in fractional order controllers for the control of flexible manipulation. And he has large experience in the field with more than 100 research papers in high-impact conferences and journals. So please, floor is yours, and I'm pretty sure it's going to be fantastic.
Okay, thank you. Thank you very much for inviting me. My pleasure to be here. I'm just sharing some of our ideas and solutions from my lab regarding soft actuators and sensors, and also robots that we can apply for real problems, right? So I'm going to start saying, when all this started from our side, because we come from the humanoid robots field, right? Which are quite rigid and quite limited, as you may know, right? So the idea is, okay, we have this, let's say, hard structure, and we want to improve some of its joints, right? Because it's clearly rigid, and in some cases it breaks, right? We have some experiments in which we can see that the robot is breaking. Apparently, there is no reason behind the breakage, but of course it is because of the hard materials composing the robot. So one day we decided why not to research a little bit on soft joints for this robot. And the first idea was to replace the neck by a soft soft link acting as the neck, right? And later we can see how this has evolved into a soft arm. And we will discuss from that solution, other solutions coming next, right? So the idea was, first of all, okay, to design the neck, the continuum, right? But also, there is a constraint for us, and we need to be sure that the solution must be, or needs to provide accurate positioning. Right? Maybe in some of the examples we can see today along the session, the accuracy is not needed, not required, but if you use it as a robot, as a humanoid, for instance, you need accurate positioning, right, of the joints. So this is something we need, and this is important for us. So we need that accuracy when positioning, and also we don't want the system to be very difficultly modeled, right? We want a very simple design model, mathematical model for the joint, so that later we can easily control the joint. So for us, controlling, accurate control of the system is very important. So let's see how we have addressed all these things, right? So what we propose is a simple design so that we can simply model with as a linear system, even if it is not. And then later with that linear system, we are proposing a specific type of control, which is called fractional order control. We will see what it is about. And so that the link can be controlled even in the case of loads on the tip, right? Imagine the situation in which the neck is free of load, but what if I put some loads on the neck? Imagine a different head, heavier, right? And the neck must, of course, support the new head of the robot. So let's see how to deal with these kind of things, right? So our first approach was to design this soft continuum, as you can see here, link, right? And this is actuated by 3 tendons. Initially, this is inelastic. The tendons are inelastic. We will see later how to improve that. And then the tendons are attached to some pulleys acted with motors. So it is as simple as I have a motor revolving, and then the tendon length is varying, right? So according to the variation of the tendon length, I have different inclinations and orientation of my joints. This is the thing, right? So, of course, this is a nonlinear system because of the nonlinear characteristics of the continuum, depending on the material we use for it, and we want to simplify the model a lot. So what we have done is, okay, Let's first analyze the configuration of the mechanism. We can identify simply with these two graphs, right? You can see there theta S as the orientation angle and theta P as the inclination angle. Imagine if you take the neck as a reference, we can incline, bend the neck and also orientate in 360 degrees the neck. This is what we want to control. So we, of course, want to solve the kinematics problem here. So meaning, if I have a particular pose that I want to reach for my neck, what is the set of lengths for my tendons so that I can achieve that pose. This is the inverse kinematics that we solve next, right? So we can simply, easily find that relationship. You can see the graphs relating the particular pose, and for each of the pose in the 3D environment, the combination of tendon lengths, we need to achieve it. And this is because of the simple design of our neck. I have here, later you will see, this idea, first idea, has been transformed into this new idea, but you can see here that one of the simplicity brought by this design is that the curvature that you reach when bending is constant. Can you see? So it simplifies the mathematical model of this, the kinematics, inverse kinematics of this extremely. So it makes the system very ideal for later modeling and control. This is what we have achieved here. So, okay, now that we have the length of the tendon, this is simply translated into the rotational angle of my motor. And then the only thing I want to do is to control the motor so that I can control the pose of the link. As simple as that, right? And we experimentally test exciting the neck with different step inputs in inclination and measuring the final inclination of the tip with a sensor. We put a sensor here, we command an inclination bending, right? We measure the real bending, and we have a relationship between the output bending and the input bending. And this is, of course, we can look for more complicated models for that, but we have tried and adapted that to a very simple first-order linear system given by a transfer function, right? In which we can identify the gain of the system and the time constant of the system. And believe it or not, this complex, because of the material link, can be modeled dynamically as something as simple as this first-order transfer function. Right? This is what we have achieved thanks to a simple design in which the material, of course, provides flexibility, but at the same time, we can face, we will see later how, right, the simplification of the model. So assuming that this is the simple model we want to control, the next thing is to design a controller for it. For us, this is an important part, right? Because I repeat, we want to accurately position the link. So here the thing is that, of course, I agree that my model is having a lot of uncertainties because of the nonlinear nature of the material I am neglecting. I am considering this as having a linear behavior. I am going to face that. And this is where, and in fact, this is what I want. I want to demonstrate that even if I am linearizing and neglecting a lot of dynamics here, I can control it. I can face that from a robust control. So this is one thing. And the other thing is that, okay, this is a neck, and I want it to be loaded by different masses and see if I can face the control problem when this happens, right? So what we have done, since we have we need a robust control even in presence of loads at the tip, you will see that, right? We have tested how the load on the tip affects the model. And we have tested experimentally the neck, and we have demonstrated that the main parameter in the model is the gain of the transfer function. That gain k we have in the numerator of the transfer function. So eventually what we need is to reach a controller that provides robustness to gain changes, right? So if we can provide that, then it means that we could put different loads on the link, and the controller will face variations and keep it in the vertical position, if that is the constraint, to keep it vertical in a neck, right? Or in any other pose. So let's see. Of course, I'm not explaining here the controllers. This is another topic, but just to mention the three main characteristics or constraints we are providing with the controller. First of all, this is designed in the frequency domain. What we want is to adjust the overshoot of the response. Overshoot meaning the balance of it, right? If it is oscillating or not, we can adjust that with the controller, right? So we will design the performance for a particular overshoot, a percentage. And then also, of course, we want to tune the velocity of the system. I want the neck to bend faster or slower. This is something I can also tune, the speed of the system, right? And the third constraint is the robustness to loads at the tip, right? To gain variations of the transfer function, right? These three constraints are achieved thanks to the use of this controller that we proposed. You mentioned before the PD controller, right, in your previous talk. And in here, what we are using is the typical PID controller. People in control field know, right? But we are generalizing the orders of the integrator and the derivator. And then so that those orders can be fractional, non-integer, right? So for instance, with a simple PI controller with 3 parameters to tune KP, Ki, and alpha, we just simply can meet the 3 constraints, 3 parameters, 3 equations, and we can reach a solution. And this is what we have done in the frequency domain. So what does it mean? It means something very simple, that if I want my neck to bend like this over passing the final value, imagine 10%, this would be the maximum overshoot for whatever the load you put. Whatever. It can be faster or slower, but the overpass around the final value will be constant. This is the robustness we are looking for. Right? So, okay, here you can see an experiment in which we have loaded extremely the neck. This is 1 kilo, and the mass of the link is 14 grams, right? So you can see how, with a robust control, we can face disturbances in which very heavily loaded, and also with a disturbance. We have the technician there, Raul, hitting and pushing the neck. You can see how it deforms, right? But very, very fast, it recovers the vertical position. And it is because of the, first of all, because of the design, but then because of the controller we are using. And this is tuned very easily as a linear system, and the controller is facing the variations and the non-linearities and mismatches we have introduced, or we have neglected mainly, right? So this is one thing. Okay, now we have improved the prototype because we wanted to use it, the link, as an arm. And this is the design I'm really showing you here. You can see the difference. Now the tendons are inside the structure, so the slackness is avoided, and it is more robust and secure, right? And you can see that the idea, the philosophy is exactly the same, but here we have patented the design, and this is because of the fact, I introduced that before, that we can bend having different blocking angles here to protect the extractor. So from the design, we can configure the design so that different angles, maximum angles, are achieved. Imagine that you are in a situation in which the arm needs to carry some loads, and you don't want the arm to bend a lot and break. In that case, you can configure the design so that these angles are forced, right? And you can protect the structure. This is behind the idea behind the patents, right? So using the same idea, the same type of control, here we can see how very accurately, believe me, this is very accurate, we can control the positioning of the arm with or without load. In the video at the bottom, you can see how for different loads we can very accurately also position the tip. This is the idea. So we are working on this, and now what we have thought is, why not to scale this and use it as a gripper, right? These are now fingers, and in fact, these are these fingers are exactly like this piece here, and we want to achieve the grasping, facing the grasping with different surfaces. It is not the same that I grasp the bow using the edges, right, like this, or using the vertices, right? So for a very fine manipulation, maybe with the vertices, it would be better, but for a huge grasping, I would, of course, prefer the edges so that the surface contact is bigger, right? We are demonstrating or studying how to demonstrate that according to the type of grasping required, I can rotate the finger and approach the object in different ways, right? Also with the blocking idea and limits. Well, we are still, this is the beginning of our project, but we are happy to see that we have some solutions already with possibilities, right? So this is also one of the approaches. And then, previous professor introduced the origami thing. Very happy to see this. This is also origami. This is the Kresling pattern for the origami. But what we do here, this is the another gripper. I have it here. Later, if you want, we can make it function so that you can see this. So the idea is to have this solution here so that, as you can see in the video, the gripper adapts to the object. I'm not really acting on the fingers, but on the origami structure so that it adapts. So imagine that you are like manipulating a sponge, right? The dynamics of the formation here couples with the dynamics of the formation here. So this is the idea, to make it more adaptable and safer for the grasping. This is the idea. We have also installed the gripper in the robot Tiago, which is a manipulator, right? So later, if you want, we can show you. And this is maybe a simple proof of concept, I agree, but the idea of it is to make the gripper to build it with self-healing materials. I don't know if you have heard of it, but the idea is, why not to build the origami with this material that I have here. This is in the envelope because apparently you cannot directly touch it. You have to manipulate it with some gloves, right? But the idea is, what if we manage to create the origami as an artificial muscle? We can also introduce it into water. I mean, there is no limitation for us because of the water environment. But the idea, what if it breaks, right, because of a fissure or whatever? So the idea, it can self-heal, which is the amazing particularity of this material. You can see in the video that this happens, right? After certain cycles, I don't know if we can repeat it or, I will do it here, from here. Yes, you can see, sorry. Let's see, running. Now running. Okay, you can see that in the edge, it breaks, right? So if the break is not that big, during a certain time, maybe some minutes or maybe hours, it depends on the material we use for the structure, right? It can recover itself, right? But if not, if it is a huge break, as you can see there, maybe we have to add extra material, heat it in the oven at 60 degrees, in this case, and recover the module. So we can use and reuse the module as many times as we need, because their functionalities are totally, fully recovered. Right? This is the idea. And we are working on these self-healing materials too. And also having, making use of these characteristics of the material, we have developed a connector. This is a connector made of self-healing materials again, and with temperature we can connect and disconnect the modules without the need of mechanical elements like attachments or whatever. Very easily and in a controlled way, using temperature control, we can attach and deattach the modules. So easy to plug and play, let's say, and heal. So this is also a part of our research. so far, what we have addressed is some solutions, right, in which the material is part of the structure of the robot, but also we can address sensor parts, sensor systems, and actuator systems. I don't know if you're familiar with probably you are, with shape memory alloys. These kind of materials are like amazing because they have a property, when you heat them, they contract, and when temperature recovers, right, they elongate again to the original form. So with these kind of magical wires, we can also, we are working on it, we have replaced the tendons, inelastic tendons of the previous neck, and here we have tested what happens if now the tendons are SMA-based actuators, right? So heating them and cooling them, we can change the lengths of the tendons, and then we can provide some movements to the neck. We agreed that the actuation, because with temperature, you know, it happens, the velocity of the actuator is reduced, is limited, but in some applications, we don't need the actuator to be that fast. And then the next solution is one case. You can see how this is an elbow exoskeleton in which the SMA, the wire, is here in the elbow, enrolled, right, in a pulley. So with temperature, controlling currents inside the tendons, we can make the arm flex and extend, right? So with applying current, we have the flexion, and then when the current is cut over, then the arm recovers the original extension. So replacing motors, right, by these kind of actuators, what we find is that the system is very, very light, and there is no noise at all in the actuation, which is a good thing for people suffering from, for instance, an ictus or with maybe depression or anxiety. In this case, we better if we avoid any type of sounds around, right? So this is one of the applications we have addressed, apart from using them as tendons for the necks and the arms we are developing. And also sensors, right? We work with a variety of sensors like this one. You can see here a lot of samples, right? We are just researching on many different types of them, polymeric matrix that we can also let's say, reconfigure using also other materials inside, right? So the thing is that since we are using bendable surfaces, right, why not to attach the sensors to the bendable surfaces and measure directly what happens there, directly, with a very flexible solution. And not just these materials, but also, well, I don't have it here, but the last one you can see here, this is carbon nanofibers tendons, right, sorry, sensors, in which we can this is in fact the next, no, it's not here, sorry. But we can measure very easily how the electrical characteristics of the material changes with the deformation. So this is something we are also researching on. And as an just to finish, more than these cases in which we are working, now we are very, very happy to see that we have an opportunity in the development of this cervical orthesis, in which what we want is to, first of all, create an orthesis very soft so that it can adapt to any neck, healthy people or maybe people with movement disabilities, right? And we want to integrate inside these type of sensors and also these type of tendons, SMA tendons actuators, so that finally what we want, what we have is a platform able to not only monitor the positioning of any neck, right, but also to be able to act on the positioning of the neck for cases in which the patient maybe cannot move the neck or need the neck to be blocked up at a particular position, right? So we are just starting the project, but we are confident that we can get a solution in which we can integrate these intelligent soft materials as actuators and sensors for a more portable, easy to wear, and also cheap solution for this kind of people needing these kind of devices, right? And well, this is all. Of course, there are some projects behind funding this research, thanks to the ministry mainly for all the opportunity given to us, right? And of course, it is possible because we have a great group behind. Lisbeth, for instance, is here, one of our now doctors that have developed, she developed the Reaper and many other things that I have shown you today. So, well, thank you to all of them. And thank you for attending the conference. Thank you very much.
Okay, so thank you very much for the inspiring presentation. So now we have some time for questions. I have many, but okay, there we have one. Marwa and Eliseo, any one and then the other one.
Okay. Thank you so much, Concha. Very interesting presentation.
Thank you.
Just a quick question. I'm interested about the 3D printing of the TBU, the conductive TBU. I'm not sure if you read the problem of the conductivity. If you have the conductive TBU and the 3D printing, the conductivity sometimes is affected. So,
yeah, it is a huge problem for us. In fact, what we collaborate with AIMPLAS, which is the Plastic Institute in Valencia. So they are the ones leading with these kind of things and problems, also IMDEA materials. So we have as partners these people very in the topic, right? So they somehow tell us how to face these kind of problems, because of course conductivity, the noise in the measurements, this is something difficult to face, right? But well, how you weld the connectors, how you filter the signals, this is something we are, and Lisbeth, she's here, and she's the one that, who has faced all those problems. But eventually we have reached good solutions for that, and let's say that the material is manageable as a sensor, somehow giving us repetitive measurements and showing possibilities to be used as a robust sensor for the applications. But it depends a lot on the materials we are using, and well, and yeah, there are many things affecting, right, the robustness of the material as sensor. This is of course the main one, I would say. Thank you, very interesting question.
So, following one.
Okay, good presentation, thank you. My question is more related how you are handling with the non-linearity of the SMEA and hysteresis for the material, and if they are suitable from underwater robots for sure.
Yeah, well, I totally agree. This is, as you may imagine, very non-linear. We have hysteresis there. So what we use is a controller, specific control, to avoid that, to manage these kind of things, non-linear control for that. And if you are interested later, I can show you some papers in which we deal the problem specifically. But we can manage, even with fractional order controllers, we can, in the linear part, we can control it like this, and we can compensate the linear part with a bilinear controller. We will show you later if you are interested. And regarding the fact that this is underwater, well, we are not experienced this kind of applications so far, but I must tell you that I don't know if you know octopus. This is an octopus developed in Pisa by a research group there. This is one of the main soft robots as a reference when we think of soft robotics. And it is acted by SMAs, and what they do is to introduce the octopus in the water, and the actuations, of course, is outside the water, right? But since for SMA, what we need is a simple power control cage, we can protect that for water, environment, and we don't think this is a real problem, because the SMA would be inside a capsule, and also introduced into the material of the robot, so it is protected by the shape, by the body of the robot. My
well, maybe in the meantime, I just got an idea now. I just want to
Yeah,
share.
please.
Because in the end, somehow you are controlling like kinematics.
Yes.
But what about material properties? So I was thinking, just to link with underwater, that it will be ideal if you put all these systems with, there's something called magnetorheological fluid.
Yes.
Where essentially it's perfect because it's incompressible, so it can go underwater, keeping the pressure. So in the end, by controlling the current for generating the magnetic field, you can control and adapt the stiffness, right? So I was thinking about these first ideas you were showing, right? Doing like that, and then with the damping. So I was thinking that maybe this is kind of ideal, right, for this kind of applications, because you are directly controlling the viscosity. So
yes, it is, and in fact, this was one of the first proposals we had. But we, as a first step, we decided to use a simple continuum material as a whole, easy to bend with tendons, right? And let's see later if we can improve using these kind of approaches you're offering us, right? But of course, this is something we considered. And I totally agree that in here, the nonlinearities of the material, how they affect the approach, because they affect. The thing here is that after several, I must say, a lot of them, cycles of performances, right, of the joints, we can observe, maybe not physically, but visually, but of course the material somehow is affected, right, and deteriorates, right? So it happens that when it recovers the original position, it's not exactly the zero position, right? You can see that because of the nonlinearity of the material, something happens in every cycle, right? This is why we are introducing now artificial intelligence.
Okay.
Because in our control, we want to avoid data, meaning we need the analytical model for it, because we are happy with having the analytical model, right? And also from the model, we can design very easily all our controllers, right? And it works. But if you want after certain cycles, right, when something happens, because robustness here is for, okay, I have the nominal system and slight variations around the nominal system, not all type of variations, right? So if something happens in the structure leading to a different dynamics, then I would have to retune again the controller, recalculate the model and retune the controller. With artificial intelligence, we can do that in time, online, right? And we can face the problems. And we are now testing these approaches on the real necks and arms.
Because when you are thinking about non-linear, you're just thinking in elastic terms, because also you have non-linear elastic terms there, viscoelasticity and all these things.
Yeah.
So you are also...
Yeah, everything.
Okay.
So, but following your idea, we wanted just to have a very simple design. Let's see if with a simple assumption of the model and what is inside here, which is not that simple, right? We can face at least a first control approach, right? Very accurately, or at least we can position the joints accurately for a accurate grasping or positioning of their joint, and we are quite happy, right?
Okay.
I don't think we need to make it more complex if somehow it works for certain applications.
Great. Niels?
Yeah, thank you very much for a very nice presentation.
Thank you.
A lot of interesting examples, and coming from structural optimization, I'm sure you will see that from tomorrow morning, there's plenty of room for collaboration. But I have a quite practical question regarding the actuation of the arm. So, and this is sort of tied to the question from the gentleman down there. Is it possible to actuate quickly enough to actually make useful hand movements and arm movements with these SMAs?
Not that accurate, I agree. For that case, because it's a nonlinear material, it takes time to control it. Sometimes if the precision the precision requested is very accurate, maybe it's not the best actuator, right? For the neck, we have demonstrated that we can accurately act, but we haven't yet integrated these kind of tendons in the arm. So this is something we still have to do and see how it works. Because now with gravity, and the nonlinearities of the material, let's see how it works. I assume that we will have some problems there, right?
So related to underwater robots, it would be a slow swimmer.
Yes.
And maybe.
Yeah, of course, for these kind of applications. But since we want to integrate that into the humanoids, and so that we can provide an accurate grasping and manipulation, we still have some limits for some type of actuation.
Any other question from the audience? Okay, Fabrizio.
Very nice talk.
Thank you.
I was quite actually, taken aback by how efficient the fractional order derivative control system you are using. Is there any limit using fractional order control in terms of system and materials? Because I assume that you need to guarantee some consistency of higher order derivatives to make really fractional order control work.
The idea, if you have a transfer function to control, right? As a first side, we could say that the fractional order, you can find a fractional order controller for that transfer function to be controlled, whatever the specification. Meaning, even if the phase margin, for instance, you want to get is very high, because of the freedom of selecting the orders of the derivative of the integral, you can get that number, for instance, 2.3, allowing you to reach that particular frequency specification. I don't know if I am answering your question.
So you could use a fractional order control on any type of system, you say?
As far as this is linear. With this technique, the idea is that the system is linear.
Thank you.
And at some point, I guess you can linearize.
But of course, you can also use it for nonlinear systems. But with these tuning techniques I am proposing, the system is linear. Mm-hmm.
And if this is not linear, you can just like
linearize
part
by
part
zones, and that's
right?
it. That's it. This is what we do, in fact.
Yeah.
Or use adaptive control. So for every different region you're approaching with your joint, you recalculate the model and retune the controller parameters.
Mm-hmm.
And it is working perfectly well. But you need to linearize somehow and recalculate the linear behavior so that you can retune the controller later. If you want to do it also with a small computational cost, which is also important.
Great.
Okay.
Any other question? We already
Very
have a lot.
interesting questions. Thank you very much.
Okay, so let's
Thank you.
again.
Thank you.